Right. Hello, everyone, and welcome. This is the first day of CSE 5606. Hopefully, you're all in the right place. This is high performance computer systems. My name is Doug Shook. You can call me Professor Shook. That's absolutely fine. I'm not seeing too many familiar faces, which is probably, good reason for that. I have been at WashU for a long time. It's actually my 15th year teaching here. I'm a teaching professor, which I think I might have already said. But I'm also an alum. I went to grad school here and actually took this class probably about 15 years ago. And since then, I've taught this class. I think this will be my, can't remember if this is my fourth or fifth trip through this class, but I've definitely taught it a few times. It has been a few years since the last time I taught it, but I'm really excited to teach it again because most of the time, the reason why you don't see me too much is because I'm teaching the intro class. I'm teaching for loops and if statements to first years and um, things like that. So honestly, I'm really looking forward to this class. This is a real treat to talk about some meatier stuff with some more substance, right? I'm not to say that I don't like that part of my job, just nice to kind of mix it up intellectually every once in a while, right? Some other things about me, just to give you some more personal history. I'm a musician. I play the drums. So if you want to talk about music, that would be great. I also love video games. I speedrun video games. So that's another topic that I can chat your ear off about for hours if that's something that you are interested in. I'm also into competitive jigsaw puzzling. That's my recent obsession. So I can solve a 500-piece puzzle in about an hour. That's pretty good. Pros can do it in about half an hour though, so I still got some work to do. But yeah, I'd love to chat with you about any of those things, outside of class time, if our interests line up. But as far as this class goes, so today, probably not going to be too much of a surprise. We're going to go through all the syllabus stuff and explain the structure of the class, but we're also going to talk about some content as well. This being a summer class, I want to make it clear right off the bat that um, I am following the same general format that this class would take in the spring or the fall. But the time constraints just make it tricky to get to everything. So some compromises have to be made. We might not make it to every single topic or cover things in quite as much detail as we would in a 15-week semester because we only have 8 weeks. And with that in mind too, I'm also kind of covering 2 days roughly worth of material every time we meet. But the class time isn't exactly twice as long as the class time during the semester. So that presents some logistical challenges as well. So, just bear with me. Summer classes are kind of like that. That's just sort of the nature of the beast. I do want to make sure you're aware though that I'm not trying to dump tons of stuff on you. I hope I'm not being unreasonable in my expectations. I've tried to, whittle things down, simplify things to keep in mind the fact that we only have 8 weeks instead of 15, right? So not going to have as much time to get through homework assignments, for example, and things like that. If you're ever facing those kinds of time pressure, if I'm wrong about my expectations and what I'm asking you to do is unreasonable, please talk to me about that. I'm willing to adapt, willing to adjust. I'm not trying to make this a miserable experience for you. Quite the opposite, actually. I think if done right and done well, we're all going to have a great time this semester and learn a lot over the next 8 weeks. And I'm, again, really, really excited to be here with you running this class. So today, what we're going to do, and actually just some basic classes, I'm going to go through the first topic. It'll probably take me an hour 20, and then we'll take a break. I think 2.5 hours is too long to sit without some kind of a break. So every class we will take 5 to 10, stretch our legs, go to the bathroom, grab a glass of water. Also want to make it clear to y'all too. Class starts at 5:30 to 8. I don't know about you all, but that's dinner time for me. So, if you want to bring some food to class, I don't have a problem with that. Just please be cognizant of your neighbors. If you bring in tuna fish, I'm, maybe not going to be thrilled about that. If you're crunching away on a bag of Doritos the whole time that I'm talking, probably not going to be too happy about that. So, use your discretion. Try and bring foods that aren't going to disrupt the class too much, but we're human. We got to eat. So bring a snack, swing by Taco Bell or something on the way if that's what you need to do. Um, I certainly understand and want you to feel comfortable while you're here in class. So let's go ahead and hop in. I'm going to pull up. Obviously, this is the syllabus, which is the first thing you're going to see when you hit Canvas. Actually, everything is on Canvas. There are no other websites that I'm going to be using. I mean, I might, of course, talk about other things online and stuff, but as far as the class goes, course materials go, everything is on Canvas. So I will try to get through this as quickly and painlessly as possible. Although this class does have kind of a different structure. That's one of the things that I actually really like about this class compared to some classes. You can actually see too on the calendar. I've already uh, scheduled out the whole summer, all 8 weeks. So all the due dates for everything is already there. That's not to say, again, that some of these things might need to shift or change. As I said before, I'm willing to adapt, willing to be flexible, should the situations demand it. But this is what I'm going to start out with as my plan, and I'm going to stick to this plan as closely as possible. And if things need to change, we will. But just want you to know that you can find all the slides and stuff right here on the calendar. I've already posted like the first couple weeks of slides. So we're going to start off with our introductory slides, which is syllabus stuff, but also some non-syllabus stuff as well. My email address, which we already know. Scheduling this class really unfortunate. Workday is very unfortunate. You probably already knew that as well. My office hours over the summer are by appointment. I'm not here every day like I am during the semester. I'm really only on campus for the Monday and Wednesday evenings are when I'm physically here. So yeah, welcome. If you want to meet with me in person, immediately before, probably preferably before, because 8 o'clock is already kind of late for an old man like me. But I will say a few minutes after. That's what works for you as well. If you want to meet with me other times, then probably going to recommend Zoom just to keep things simple. As I said, I'm not on campus most days. But please email me. Please email me for anything. There are no TAs. I'm it. I'm your guy for this class. So I'll be doing all the grading. I'll be answering all the questions. And I'm totally fine with that, to be clear. That's not something that I'm concerned about at all. That's what I'm here for. That's what I want to do for you. So if you have questions about anything, email me. If you're confused about anything you see on Canvas, email me. I'll help you out. If you want to meet with me, shoot me an email. We'll set up a time either in person or on Zoom to figure it out. We do have a textbook for this class. It's an open source text. I absolutely love. There's a link to it on Canvas. There are a few topics that are from the text that we're going to cover in class, but we're probably actually not going to cover everything that's in that textbook. A lot of the sources that we're going to be using in this class come from the literature. So we're going to be talking about papers in this class quite a bit. Published papers on the topic, which we'll get into a little bit later as I get to the next part of the course structure. So as far as what you are going to be expected to do, as far as your workload, there are going to be programming assignments. They are going to be one due approximately every 2 weeks. You can see that on the calendar. So there's 8 weeks. We've got 4 assignments. I mean, you can do the math, right? There's one about every 2 weeks or so. We're going to be using C++. That's not a coincidence. That is by far the most common language that you're going to see used in this space. So it's a very natural choice. And we're also going to be talking about some very commonly used libraries. In fact, those are the big 3 right there that you're going to see on the homework assignments. Pthreads, OpenMP, which is a parallelization library, and MPI. We're going to talk about actually give you a quick and high-level introduction to all 3 of those a little bit later on today. Have any of you worked with any of those yet? Which one? A little bit of Pthreads. Okay, yeah, Pthreads is probably the one I would most expect to hear some people have experience with. OpenMP and MPI, I think, are the real heavy hitters up there. But Pthreads also worth talking about as well. And so as far as the programming assignments themselves, I'm going to give you some code to start with. So you're not necessarily going to be writing things from scratch. Our interest in this class is all about performance. So I want to understand the performance of the code. Specifically, what's limiting the performance of this code? Why isn't it going faster? What can we do to fix those kinds of problems? You might need to do some refactoring. or make some edits and adjustments to that code to try and, show that the performance can be improved using certain techniques. But rarely, I don't think actually on any of the homework assignments, I'm going to ask you to write something completely from scratch. So with that in mind, the programming is moderate. You're going to be reading code probably more often than you're writing code in this class. So from that perspective, programming knowledge still will be very useful in this class. You can work in pairs on the homework assignments. I'll go through that in a little bit more detail on the next slide. The other main part of this class are presentations. So this class is actually, in my opinion, half traditional class with lectures and exams and half seminar. So what that means is that you are going to be expected to make two presentations, one about halfway through and one at the end, where you pick a paper related to the space of high performance computing, which is actually a fairly broad space. I'll show you some examples of that a little bit later on, and then present that topic to the class. So being able to read papers, digest them, and present them is a very important skill. You'll also be asked to critique your peers' presentations. So give feedback. And that'll be part of your grade as well. The feedback is, very simple and direct. You get credit just for doing it, right? And then there will be two exams. Again, one about halfway through the semester and one at the end of the semester. But they are open book, open notes. I'll actually talk a little bit more about that in a slide or two. As far as grading goes, here's the breakdown. So you can see this is on Canvas as well. Assignments are worth about 20%. Your presentations are worth 20%, so about 10% each because they're given two of them. And then the feedback that you provide is, basically a participation grade. And exams are going to be 25% each. They are non-cumulative, so it's not comprehensive. Exam 1 is over the first half. Exam 2 is over the second. It's very straightforward, very simple. One thing I want to note, this is a graduate level class. You can see that all 10 of you who are registered right here today, which is wonderful. I don't want to have to take attendance in this class. That is not something, especially at the grad level, I feel like should be necessary. But that being said, if attendance starts dipping, I'm telling you right now, I will start requiring attendance and I will start taking attendance. And if I have to, I will insert an attendance grade into the class. I really hope I don't have to do that. But you all being here and participating in the discussions, participating in presentations is such a critical part of this class. You have to show up. And that's not to say that perfect attendance is expected. I know people will get sick or have other stuff going on in their lives, personal things. If you miss a class or two, not going to be a deal breaker. I'm just saying on average, if I show up and attendance is, 50% or less on a regular basis, I'm going to start having some things to say about that. So just fair warning about attendance in this class. But you're all adults, you're all grad students. I really don't think we're going to have those kinds of problems in this class, hopefully. All right, let's talk about programming assignments in a little bit more detail. The way that these assignments, I already kind of mentioned, given some code, has to modify it. We're specifically concerned with performance, though. So I'm not really all that interested in how well the code you write, like how well it's written necessarily. I want it to work, obviously. I don't want it to be busted or filled with bugs. But you're not going to be graded on, how pristine your code is in this class. It's not what this class is. You're going to be graded more on the your analysis of the performance of it. So, for example, the first assignment is really just kind of a warm-up assignment to get you familiar with these kinds of ideas. How do we measure performance? What are the kinds of tools that we use to measure the performance of our programs? I'm expecting when you complete the assignment, and I'll actually show you the first assignment here in just a few moments, that you're going to submit what looks like a mini research paper to me, complete with figures. I'm expecting you to do some data collection, right, to justify the performance of the program. Here's how the program works with one core. Here's how the program works with two cores. Here's how fast the program is with four cores, et cetera, et cetera. So You're going to be designing these little mini experiments and then collecting data and then analyzing the results. That might mean that sometimes the results don't do what you think they're supposed to do, right? That's research. So tell me that. That's not necessarily a bad outcome. Sometimes learning how things don't work is just as valuable as learning how things do work. So in that sense, this class is very flexible, very open-ended. You'll see the assignments are very flexible and open-ended. You actually don't have to complete everything that's listed on the assignment. It's more of a menu that I'm asking you to pick and choose a few things from. I might require everybody to do one or two of the things, but then you'll have a choice, an option to forge your own path and pick your own direction for the remainder of the assignment. You're all grad students. I think you are worthy of that responsibility, right? Again, this is meant to kind of get you used to the kinds of research and things that we care about in this domain. Eventually, we're going to start using the cluster. So we actually have a cluster on campus. I believe it has, I don't remember the exact number of cores. I want to say it's in the hundreds, if not low thousands of cores. I don't think we'll be allowed to use that many because they only have a certain number of them reserved for academic purposes. The rest are reserved for pure research purposes, but we will get our hands on enough cores to do some interesting things in this class. There is a possibility for us to do some GPU programming in this class. It kind of depends on how things go a little bit. But most of the code, I think, will actually probably be CPU-based C, C++ kind of code. Although I'm very open to proposals. If you really want to do some GPU programming and you see a good way to work it into assignment, talk to me about it. I'm very interested in having those conversations with you. And the best thing for you to research in this class, in my opinion, is what you're interested in. So if you're interested in a particular topic, as long as it fits in the realm of high performance computing, I'm going to be excited about that. I'm going to be thrilled that you're interested in that. So just a little warning, right? Because the data collection is such an important part of these assignments. If you get your code functional the day it's due, that's a problem because that doesn't leave you time to run a bunch of trials, collect a bunch of data, and create the plots that are necessary to display that data and write the analysis that's required to tell me what the data is showing us. So yes, writing code is part of the assignments. That should be the first thing that you get knocked out of the way. Make sure you leave yourself time to do that data collection piece. I will actually probably give you some time in class occasionally to, especially when homework assignments are first introduced, I will almost always give you some time in class to get started, get set up, make sure everybody's at least moving off in the right direction. But of course, I'm happy to meet with you outside of class if necessary, if you have questions on the homework assignments. So yeah, actually, I already kind of mentioned this. Each assignment has lots of questions, but you kind of get to pick and choose. I want to show you an example of that. So let me switch back to Canvas real quick. I posted the first homework assignment already. I would encourage you to look at it. I would encourage you actually maybe to hold off on starting it until Wednesday, because on Wednesday's class, I'm going to be talking about some very specific things that I'm going to be looking for in these reports, especially as it regards to presenting your data, presenting your experimental results. That's one of the topics that is on the agenda for Wednesday. So once we're through Wednesday's material, you'll be all set. You'll be all ready to do the first homework assignment, but I just kind of want to give you a feel for what's coming up. Here is the code that will be provided. It's a vector matrix multiplication operation. And then here is your menu, right? There are 10 prompts here, but you'll notice, or I took the slides, but on the slide it said, if you're working by yourself, you get to pick 3. Do the 3. If you're working on a team of 2, I expect you to pick 5. You can do 5 of these 10. Right, so you get to pick and choose, although I do think, do I actually require you to do, oh, on this assignment I don't say, yeah, on this assignment I actually didn't say that, on some of the assignments I might say something like, you have to do number 1. everybody has to do number one, but on this one, I didn't even do that. On this one, it looks like it's just a pure free for all. So again, lots of openness, lots of flexibility. If you're grad students, I think that's a reasonable expectation. Um, so yeah, we'll talk more about this homework assignment in a lot more detail on Wednesday, but I just kind of wanted to give you a feel for what that looks like for now. Let me go back to my slides here. Should open that in a new tab so that I don't have to keep switching back and forth. Sorry about that. And yeah, I think I already mentioned most of this as well. The stuff about error bars, like Gaussian error, things like that, that's Wednesday. We're Wednesday, so don't freak out too much about that right now. I'm going to give you some very concrete suggestions on how you should be presenting the data, how I would love to see you presenting the data on these reports. That's the topic for Wednesday. And then you'll get feedback, and the way that the feedback is going to work. I'm assuming you're all newish to this, right? That's why you're taking the class. So the first homework assignment, not going to be graded heavy-handedly at all. You'll get feedback if there are things that I think could be improved or need a little bit more work. I'll be sure to point those things out to you. I'm not gonna be slashing off tons of points for them on the first homework assignment. If I have to tell you something more than once, however, well, that's probably when I get closer to slashing off points. I don't expect you to be perfect every time, but I do expect you to receive feedback and adjust to it. I think that's very reasonable expectation. So what that does mean is that the grading, the tightness of the grading probably will get progressively more and more as the semester goes on. But I'll be grading all of them, like I said. So you'll get hopefully very consistent feedback across all four of those assignments from me. And in terms of, again, I don't really necessarily care as much about the code. The code does matter, right? Obviously. You don't need to give me the whole shebang, though. You can just give me the important parts, the important bits in your report. You dump the whole code in an appendix. I'm not going to read it even if you do. In fact, I would say that these reports, brevity is a good thing. You need to say what you need to say and get the heck out of there. If it's 20 pages long, that's a red flag for me. That feels to me like you're probably just trying to use a bunch of filler and say a bunch of stuff that doesn't necessarily need to be said. So, not to say that there is a page limit. That's a hard thing for me to define. Easier for me to define too much, too little, a little bit trickier, because it depends on the questions that you choose, how many of them you're choosing to do. So, just kind of keep that in mind as you go. Are there any questions about the homework assignments before I move on? Cool, awesome. All right, let's talk about the presentations a little bit more. So this is going to be you picking a paper. To help you with this, right? I have already posted on Canvas. If I go back to the proper tab, I've already posted right on the syllabus a list of papers. So candidate papers and other subjects for presentations. So here's a list of papers that are from, you can see recent conferences and publications regarding high performance computing. So any of these are fair game. If you want to pick one of these are basically pre-approved as being okay for presentations. You'll notice they're all fairly recent. So and that's the field we're in, right? High performance computing is always bleeding edge, top of the line stuff. That's what we care about in this class. So if you want to pick a different paper that's not on this list, I don't have a problem with that. In fact, I believe I also linked to some common conferences. I thought I did. Maybe I forgot to do that part. I'm sorry. Oh, here, yeah, down here at the bottom, you can find some links to some conferences. So, any conference proceedings, few-ish years, right? So I wouldn't go anything more than 5 years is probably an instant no-go. Even five is probably pushing a little bit in this field, right? It moves fast enough to where even something 5 years ago may not be quite as relevant these days. But recent papers from these conferences, I think, are all pretty much fair game. If it's not on this list, though, you do need to get approval from me first, which just means sending me a link to the paper you're interested in, and I'll give you a quick thumbs up or thumbs down. It's as simple as that. Um, I also, let me get back to my slides here. The presentations I'm expecting to be about 30 minutes in length. That means that we can do 4 of them per class period. So there are 10 of you, which means that it will take us 2.5 class periods to get through all of the student presentations. I've actually already marked them out on the calendar. So one of the things that you'll need to do fairly soon, actually, is send me another email letting me know which day you would like to present. So looking at the calendar, you can see that I've got the student presentations, the first round set for the 22nd, the 24th, and the 29th with, I'm expecting 2 students to go on the 22nd and then 4 students to go on the 24th and the 29th. So, please take a look at your calendar. Please, if you already know you want to go on a certain date, send me an email, get it locked down. It's first come, first serve, right? And if I don't hear from people probably by next Monday or next Tuesday or so, I'm just going to start signing them out myself. So if you want to pick the day, think about it over the next week or so, shoot me an email. You don't even have to have your topic decided to claim a day. You can tell me your topic later if you want to. I don't have a problem with that. I do want to know your topic ahead of time. You can't spring your paper on me at the last second. That's not cool. But if you want to send me an email and lock down your dates today, and then send me another email next week after you've had a chance to go through the papers and pick one, totally fine, but not a problem at all. But yes, that's so you can actually very clearly see the division here, right? The first 2 weeks of the class, that's my job. That's me introducing topics and discussing these topics with you. And then the seminar half is, kind of this half down here, capped off by the exams, which we'll be talking about here momentarily as well. So yeah, each student's going to do 2 presentations and exams. We're also going to submit 3 exam questions. It means that you're going to be asked about these presentations on the exams. Now, I know you all don't have a lot of practice writing these questions, right? I do. Been doing it for quite a while, so you may not see the exam question in the exact format that you submitted to me on the exam. I might tweak it a little bit. I might make some adjustments to it based on my experience. I'm the one who has to grade it, so I might make some adjustments with that in mind. But I certainly will at least use these exam questions that you give to me as topic areas that will be included on the exams. And you better get your own exam questions right. Like those are freebies, right, on the exams. And any freebies, basically, for those ones. So everybody's gonna at least get, their own exam questions correct. And these exam questions can be in any format. So if you want to do the exam will be a mix of true, false, probably not a whole lot of fill in the blank, multiple choice, maybe a few multiple choice, true, false kinds of questions, and then maybe a few longer form questions where you might have to do some basic pencil and paper kind of arithmetic. Nothing that is extremely number crunching, although, well, I'll talk about that when we get to exams. Anyway, and then the other part of it, of the presentations is feedback. So you will not have to give feedback on every presentation. I'm only going to ask 2 or maybe 3 of you to give feedback on each presentation. And that feedback will go through me. So I am not going to turn around and give the feedback directly to the presenter from you to them. It will be filtered through me, mostly just for to maintain anonymity. I can't say that word today. Sorry, you know what I mean. Mostly just to keep it anonymous. Um, I have never had extremely disrespectful feedback come through in this class. We've not had that problem, fortunately. Other classes, unfortunately, I have had that problem. But should that happen, that will be filtered for me. I'm not going to allow that kind of, if anything comes through that's extremely unprofessional, disrespectful, that is not going to make it to you. That is not going to happen. That's my job to make sure all that stuff gets filtered out. So yeah, and of course, I will also be providing my own feedback. I will provide feedback on all presentations. That's kind of my job as the instructor of the class. Any questions about the presentations before we talk about? I think we're going to talk about the exams a little bit more after this. Yes. Oh, yes. Thank you. Thank you very much for asking. Yeah, the feedback will be on Canvas. It'll be probably just a text box, right? And the feedback that you're asked to give is the same for every presentation. There are like 3 questions. Don't remember them exactly off the top of my head. I think one of them is like, what did this presenter do well? What could this presenter improve on? So things like that. And it'll be assigned to you on Canvas, and it's so short. So you'll have, a couple days maybe to fill out the feedback form once it's been released to you on Canvas. Although, again, during the spring, I would probably be much more of a stickler on due dates and things like that. Over the summer, I'm less so. I'm more loosey goosey. So if you have problems with getting the feedback on time, we can talk about that. We can work. Hopefully that answers your question. Yeah. Any other questions about the presentation piece before we continue forward? This is actually one of my most favorite parts of the class because it allows you to direct where we go. In fact, in past semesters, I use the topics that you all pick for the student presentations to help me decide what topics I talk about in the class. Because if a lot of you are picking topics, papers that are all about a certain topic, I'm going to draw the conclusion that you all are interested in that thing. And I'm going to look for more ways to incorporate it into the class. I think that's one of the great things about teaching this class. Um, there is not necessarily, there are some things that are kind of set, right? I do have some parts of the path that we're definitely going to do, but there are other parts of the path that I will gladly mix and match and swap out if you all want to go in a particular direction. I think that's great. I think that's how graduate level classes should be run, right? So um, please pick topics that are interesting to you and let me know what you're interested in as well. All right, I think I already covered this stuff. Yeah, I already covered this stuff. Oh yeah, I didn't cover this part. Just as a little carrot, because nobody ever seems to want to sign up to go first. If you do sign up to go first, keep in mind that you are kind of the trendsetter, right? Which means that I'll take it a little bit easier on you in the assessment. I don't think that's a reasonable thing to do. So just as a little carrot to get you all to try and sign up for dates. The earlier you go, the more likely I am to be gentler in my assessment of your presentation. And I will update if somebody claims a paper, I'll be sure to update that on Canvas because obviously I'm not allowed 2 people to present the same paper. So just keep an eye on Canvas. It is first come, first serve. So if you see a paper you really want, let me know as soon as you know so that you can claim it before somebody else does. Okay. All right, the exams. They're going to be in class during the regular time slot. I'm going to hold a review session for the first hour or so of class that day, where we go over basically all the topics that we've covered in that section of the class. You'll then have the rest of the class time, which should be 90 minutes or so. Yeah, because we're 2.5 hours. Yeah, you'll have 90 minutes to do the exam. I don't think it's going to take you that long. I really hope not. I think if you come to class, you pay attention, not going to take you anywhere near 90 minutes to do the exam. But that's how much you'll have. It's also an open book and open notes. You can't talk to your neighbors. When I say open book, open notes, I understand that the textbook is online. I don't want you, so, using your laptop to look at your notes, if you take notes on your laptop, I'm actually okay with that. What I'm not okay with exams, especially, is any use of generative AI or any AI basically at all. So if I see ChatGPT or Claude or whatever open on your laptop during the exam, you and I are going to have a conversation about that. That is strictly forbidden. If you want to bring your laptop to look at your notes, 100% okay. 100% okay with that. You want to bring your laptop to have the PDF of the textbook, totally okay with that. Not a problem at all. But I definitely will be going around and looking. You cannot use phones because I cannot adequately monitor phones. Screens are too small. You see what's going on. If you want to bring a laptop, something with a big enough screen where I can see what you have open on your machine. But I'm very serious. I don't even want to see a tab in the background on ChatGPT or whatever during the exams. That is an instant academic integrity issue as far as exams go. So, um, yeah, and as far as what else could be on the exam, the lectures, of course, stuff that I talk about in class is fair game. Assigned readings, which honestly there aren't a ton assigned readings from the text. The textbook still, though, is a very good general resource. I would encourage you to take a look at it. The programming assignments, so anything you do on the homework assignments, also fair game for the exams. And as I already mentioned, the contents of the presentations presented by you all are also fair game for the exams. Any questions about exam stuff? Good, great. All right, let's talk about academic integrity real quick. I already kind of mentioned some academic integrity stuff as it regards to exams. Maybe I scared you a little bit about my stance on Gen AI. I'm actually, I would say, mildly positive about it. I'm worried about power and water consumption aspects of it, like many people are. But in terms of academic usage, I certainly see a lot of value. So, in terms of using it on my homework assignments, you can, but there's a right way and a wrong way. So, if you need to use, ChatGPT or something to help you clean up the language of your report, I don't have a problem with that. If you use ChatGPT to write the whole report, I have a problem with that. So, the ideas need to be yours. The conclusions need to be yours, right? If you need ChatGPT to help you express that, that's okay. Especially, I don't know if it's true or not, but very often, sometimes English is not people's first language. So, very understandable that you might want some extra help expressing your ideas, but the ideas must be yours and your partners, which is another very clear line. No groups larger than two, period. Not even going to obtain it. If you ask me, the answer is no. So showing your work to another group also very much against the line because that's basically then expanding your group out to a larger group other than two. So um, try to. I'm trying to treat you all like the adults that you are in this room. Again, I don't anticipate having any kinds of academic integrity issues with generative AI. I'm also not an idiot. I think I will have a pretty good idea if you use ChatGPT or something to crank out your full report, and I will call you in to talk to me about it if I think that is in fact the case. I don't want to have that conversation. You don't want to have that conversation. Please just be smart about it. I know I'm old. I know I took this class before ChatGPT existed, but I wrote all of my reports myself and I'm fine. So, you know, you can do it too. I promise you, you can. If you're concerned about it at all, about running into academic integrity issues, that's certainly what I would recommend. But you are all adults, and I'm not going to deny the utility of generative AI. So please just use discretion is all. And if you're ever unsure, come talk to me about it early before you do the thing, not after you do the thing, so that we can have a conversation about it. I like to think that I'm reasonable. I want to help you as much as I can, so I will always hear you out. That being said, it is a graduate level class, and so the standards are much higher than it would be intro class, for example. So any kinds of academic integrity that crosses these lines will be dealt with according to the published academic integrity policy for graduate students. Um, all right, that is all of the logistics. I've covered it all. So before I actually hop into something that is much more interesting than course logistics, I just want to pause one more time to see if anybody has any questions about what's expected of you in this class, what's coming up in this class, things like that before we more interesting. Yeah. Yeah, just let me know what date. So if I look at my inbox and I got, 5 emails all asking for the same day, take the first four and email the fifth person. Sorry, please. Yeah, only first come, first serve. Yeah. Uh, well, the idea behind the presentation is that you will be distilling that paper and presenting it to us, right? The people in this room will not have read that paper, with the possible exception of me. Although I have not read all of those papers. I'm actually, some of those are still on my to-do list, right? I have read some of them, not all of them. So the idea is that you are presenting specifically on that one paper. Yeah. Mhm. And again, I also want to make it clear too that 30-minute time limit. There will be some Q&A afterwards for another 5 to 10 after that. Um, I think we do have enough time to do that. But also too, some of those papers, I mean, if you pick like a survey paper that's gigantic, for example, getting all of it done in 30 minutes may not be a realistic expectation, and that's okay. That will require you then to prioritize, right? Here are the parts that I think are the most important, and if you don't get to section 3.4, well, okay, I understand. That's not necessarily a problem. Part of presenting these papers is, you telling me what the important parts are. That's part of what I'm looking for. Are you able to do that effectively? Are you able to read a paper and pick out the important parts? That's an important skill to develop. Any other questions about expectation logistics? We talk about computing stuff. All right, great. Fantastic. So let's talk about high performance computing. That's what we're all here for. I'm here to talk about assignments and exams all day, although that is part of the class. Let's set up an example. Why we even need high performance computing, why we even need to talk about super fast performance in the first place. The classic example is weather forecasting. We have hundreds, thousands of weather stations all across the country, collecting large amounts of data about temperature, humidity, pressure, all of those things, right? So let's set up a simple example. This is actually going to be a much simple example than what we're actually doing in real life, but that I think presents an even more compelling case for why we need high performance computing. In order to forecast just for North America, we're just talking about one continent. Of course, we could expand this over the whole globe if we wanted to, but we're just going to talk about North America. In order to do a proper weather forecast for the continent, we're going to set up a cubic grid. So basically, think of setting up a flat horizontal two-dimensional grid that is, 0.1 kilometers per side. These numbers are a toy example, right? The surface area of North America is roughly 20 million kilometers, give or take. And if we want to, we're talking about weather, so we have to go up. We can't just talk about the land. We have to go up in the sky as well. So we're going to set up a 20 million square kilometer grid, but then we're also going to take it up in the third dimension, another 20 kilometers into the sky, which, to be fair, is not even really high enough to properly do full weather forecasting. We would need to go higher than that if we were being serious about this, but this is just a motivational example, as I said. Then let's assume, again, this is a very big hand wavy assumption. let's just assume that in order to forecast this weather model properly, we need 100 floating point instructions. So 100 instructions running on our computer for every single cube for every single time step that we care about. And the time step that we care about in this, again, very simple example is going to be once every hour for 2 days. So 48 time steps. We're only trying to forecast the weather 2 days ahead of now, 2 days in the future. So if we do some quick maths, some quick quick computations, the number of grid points that we have is going to be, this represents the two-dimensional grid over North America, the area of North America. This represents the vertical going up into the sky. So we have this many grid points on the order of 10 to the 14th. Who really cared about that first, right? It's really just magnitude. It's here. We're on the order of 10 to the 14 different grid points. So we're saying for the simple example that we have 100 instructions for every time step. So 100 instructions times 10 to the 14 grid points means that we've got 10 to the 16 instructions. It's a lot of instruction, right? A lot of floating point math that we're doing just for one time step. So we then have to multiply that by 48 to get our final answer. Just to compute the forecast 2 days in the future, we would need, in our somewhat arbitrary example, on the order of 10 to the 18 instructions. So that's how many, we're instructions we're saying we need in this very simple example. How long is it going to take us to run all those instructions? Well, let's do the math on that and see if we can come up with some answers. Machine A, 1 gigaflop per second. So are any of you familiar with gigaflops? Let's talk about it. Flop stands for floating point operation per second. That's what flops represents. So 1 gigaflop would be 10 to the 9 instructions per. This is what a typical ARM core would do. Where an ARM core is probably what you have like in your phone, or they even make them for laptops these days, right? That didn't used to be the case, but nowadays ARM chips are very, very, very popular. So if we're using a consumer grade chip that runs at 1 gigaflop, take us about 63 years to compute 2 days worth of weather forecasting. Well, that's very clearly a little bit too late to be useful. I would get the weather forecast for Wednesday in 2080, 2089. That doesn't help me. Okay, well, let's beef it up. Let's say we've got a teraflop. So that's not 10 to the 9 instructions per second, but 10 to the 12 instructions per second. This is an old chip, but it's one that is still commonly referenced, actually, because it's an experimental chip that Intel made that has 80 cores on one CPU die, right? So they crammed 80 cores into one CPU chip. Very impressive, very powerful machine, much more powerful than most consumer grade electronics that you'd be able to buy off the shelf still, right? But even this beefed up chip that can do 1 teraflop, we're still looking at 23 days. Do 2 days worth of forecast. Not good enough. It's too late, right? My daughter is turning 8 this week, and I'm really worried about her party getting rained out. I need to know now what the weather's going to be like 2 days from now. And obviously, we're all aware that we do have those forecasts. They do exist. So let's talk about something even beefier. And actually, let's make the example more realistic while we're at it. Because we don't just want North America. We want maybe South America too, because what's happening? That's what's happening. It's happening in Asia. That's what's happening over here too, right? And over the oceans as well. The spatial resolution at 0.1 kilometers is really not accurate enough either. We would need actually a grid that is much more dense than that to make accurate predictions. So I'm trying to illustrate that even our toy example is just not enough to do valid predictions. And we also ideally want to predict the weather more than just hour by hour. Some apps will do it every 15 minutes now, right? Or maybe even smaller time resolutions than that. And every time we beef up those parameters, that's more and more and more instructions that we're being asked to compute. But let's talk about a bona fide supercomputer. This guy, the Fugaku supercomputer, I believe it's in Japan, does 500 petaflops. So a petaflop would be 10 to the 15 instructions. Yeah, I believe. And we're sitting at 500 petaflops. So now we're sitting at roughly 2 hours. That 2-day forecast. That I can work with, right? In practice, how is this actually working? Where do the meteorologists get their weather? Are we using supercomputers to tell us whether it's going to rain or not? My daughter's birthday. Does anybody know? Yeah, probably not. Just 20 years ago. Exactly. We have had weather forecasting information for decades now. Although, I mean, you all are a little bit younger than me. It was not as good 20 years ago as it is. I think that's also safe to say. It was not as accurate. It's not as good at predicting the weather as it was 20 years ago now as it is today. And I think there's good reason for that. Are there supercomputers running weather simulations? Absolutely. Are the supercomputers running the weather simulations that we're seeing on nightly news? Probably not. Those are probably a combination of computers all working together. So actually, I would say an example of what we would call distributed computing, where it's not just one computer crunching all the computations, but lots and lots of smaller computers that are spread out, distributing that computation. And where are those computers? They're at the weather stations, of course. That seems like a very natural place to keep them. So, we do have ways of solving this problem. But the point I'm trying to make here is that it matters, right? Performance matters. I need to forecast something in the future. I have to be able to do it fast enough for that information to still be useful to me. If it takes me too long to compute that information, then what's the point? It's just a big waste of time and energy and resources. So how do we make sure that our programs can do that? Is it as simple as just throwing as much computing power at it as we can? Not really. There's more to it than that. Just because you run a program on a computer with, I think the Fugaku computer has 1 million cores. You run on 1 million cores. It doesn't automatically mean it's going to run faster, because the way we write our programs are a lot different for 1 million cores versus the 4 that I have in my laptop, for example. It's much different, right? So that's kind of what we're talking about in this class. How do we write code that is going to perform well, especially considering large-scale supercomputers? When we talk about high-performance computing, generally we're talking about supercomputers. Now, the one thing that is perhaps a little unfortunate in this class is that we don't really have access to a supercomputer. It's not something that most people have access to. There are a significant number of bona fide supercomputers in the world. WashU does have a cluster, as I mentioned, that has a few thousand cores on it, which is better certainly than anything that I own, probably better that you own, right? So we do have access to powerful machines, but if we're talking about bona fide supercomputers, those are fewer and further between, and harder works an average for me to get access to. So some other examples of problems that supercomputers have been used to address what's known as the grand challenge problems. These are actually a set of very well-known super hard problems in computing that have actually been, well, solved is the right word to use here, but some of them have had some very significant progress made on them, which most people may not consider them super difficult problems anymore, or certainly not as difficult as they used to be due to the progress that we made on them. But just some other examples of the types of problems that supercomputers have been used to help solve, and types of problems that we'll be talking about in this very class. Blood flowing through a heart. That's a fluid dynamics problem. Fluid dynamics, of course, requiring lots of computations, basically for every molecule or even every atom that is moving through a system. Requires a lot of data crunching. Uh, Tsunamis, so or any kind of ocean, uh, motion studies, right? Uh, Oceans are huge. Lots of water, lots of fluid, lots of power needed to accurately predict how that water is going to move around. Especially when I'm talking about things like tsunamis, which don't happen very often. Galaxies. So galaxies, of course, composed of thousands, millions of stars. And then there's also this stuff called dark matter that lives in between the stars, but affects how the stars move. If I want to know how, even our own galaxy, the Milky Way galaxy, how's that going to look in 100 years, 1,000 years, 1,000,000 years from now? Well, I have to plot uh, the motion, every single body in that galaxy over a period of time. It's a massive computation. A classic example of something that we want to use a supercomputer for. Physics. I'm not going to pretend to know what quantum chromodynamics is. Expertise. But my very basic understanding of it is the study of the motion of atoms. So if you're talking about any kind of physical body, going to be composed of millions, if not trillions, billions of atoms. And plotting the motion of all of those atoms, another very computational heavy thing. We already talked about climate models. That was the first example. Protein folding, another very protein folding at home kind of thing. That's another great example of a distributed system where we're leveraging, in this case, just everyday computers, everyday laptops. When we combine all of them together, that's a lot of computing power that we can use to solve very and of course, we're using traditional supercomputers to do those kinds of problems as well. This last one, oh my gosh, I kind of wish we didn't solve this problem, but we did, right? The classic, oh, I just booked a trip to San Francisco, and now Google is showing me all kinds of ads about things to do in San Francisco. I didn't ask for that, right? But it knows I'm going there, and it knows that if it shows me certain things that I'm more likely to probably buy those things or go do those things because I'm going to San Francisco. So these are all examples of past problems that honestly at one time were considered maybe not even possible at all, just because our technology, the state of technology at the time was nowhere near close to being able to tackle these problems. One that is maybe a bit more recent, maybe a bit more modern than some of the ones that are showing up here. How our brain works, mapping every single neuron in our brains. There's tons, right? I don't even know the order, but it's a huge number of neurons in our brains that are firing off. So how do we model that? It takes tons of computing powers. There have been entire computers designed specifically to solve certain problems, such as the modeling of the human brain, right? That's how important of a problem it is considered. And as I'm sure you're probably aware, there's still a lot we don't know about how the brain works. So we're not there yet, and we probably won't be for quite some more time. But we're getting closer. As technology gets better and better, we get closer and closer being able to solve these hard problems. And some problems that seemed completely out of reach, we all know are now very much within reach. When I took this class in grad school, one of the problems that was on this list was being able to do speech to text. Felt like a very hard problem. Felt very difficult. Now we've got it in our pockets, right? I can talk into my phone and it'll write it down for me. That was a very hard problem. That used to be a very hard problem to take sound waves coming out of a person's mouth and turn that into text. But we figured it out. First on supercomputers, and then as time went on, and the technology got better and better on consumer grade hardware. So really, we're looking at the future, right? When we talk about high performance computing, when we talk about the problems that we're solving in this class. And of course, the elephant in the room, LLMs, machine learning, training models. right? Every time they come out with a new release of GPT, that's not running on, Sam Altman's laptop to create that model. They require lots of computing power to create those models. Lots and lots of computing power to create those models. Will it always be that way? Probably not. I think they're getting better and better at reducing how much power is actually needed to create these models over time, which is kind of bad news for companies like Anthropic and OpenAI, right? If it gets easier and easier for us to train our own models in our computers, then what do we need them for? But that is the direction things are heading in, and there's no reason to expect that it won't continue to get easier and easier over time. So we're really, again, looking at the future, right? Imagine being able to train your own GPT model on demand on your computer in minutes or hours even. That would be revolutionary. So will it happen? I mean, to me, the answer seems likely to be yes. I don't know when. I don't know how long it's going to take, but the dam is already broken open. We already know it's possible to make these models. So I think it's only a matter of time before it gets easier. So yeah, that's again one of the reasons I love this class. Never the same class twice. We're always talking about different problems. We're always talking about different ways that people are solving these problems because we're talking again about the most bleeding edge, cutting edge stuff that we can get in this class. It makes it really fun. Such an exciting thing to learn about and talk about. So bringing it back to what we care about in this class, parallel programs exist. Imagine that, well, you said so you have some parallel programming experience. Maybe you have some parallel programming experience in some other class. We teach whole classes here on parallel programming, which is how to write parallel programs. We'll talk about that a little bit in this class, how to write parallel programs and what those look like. But really what we care about more is performance. It's all about performance. So I want to know how well things are performing or how poorly they're performing and why. What can I do about that performance? What are the knobs and levers that I can twist and pull and push to improve the performance or make it worse? Hopefully not make it worse, but hopefully to make it better, right? Understanding the impact of all the different things that go into the performance of a program and what we can do to try and make it better. That's really the essence of this entire class. So um, we're not talking about just huge machines, though. I do like talking about huge. That's one of the more fascinating things about the space. You get to see every day. Most of us are generally familiar with how laptops work. Most of us probably took an architecture class in undergrad, right? Which is fairly accurate for 99% of the laptops and computers that you see on a daily basis. These are not. These computers are not all the traditional computer architecture that is in your lap. So this is that same supercomputer that I mentioned earlier. It used to be the fastest computer in the world. So I think last year, so no, I take that back. The most recent list was published in November of last year, and that's when it was listed as number 7. So I think it might have been the year before, 2024, when it was actually the fastest computer in the world. Which, speaking of, this is a great time for me to take a little detour and show you that there actually is something called the Top 500, which is, um, as the name implies, a list of the 5 fastest computers in the world. So they track this and they publish this list twice a year. They publish the list every November and every June. It's June right now. They actually have not published the list for this June yet, but you better believe as soon as they do, I'm going to be excited to pull it up and talk to you about it, see what the differences are. It's absolutely fascinating. But as of today, the most recent list, which you can see, is from last November, 2025. So, taking a look at that list, we'll see that there's Fugaku, that one that I was telling you about. And they list for these machines how many cores they have. And then these are 2 different ways of measuring performance here. Notice these are in petaflops. So It's that flops term that I mentioned. Actually, the way that they come up with these characteristics, there is a benchmark, specific benchmark to compile this list. It is called the LinPack benchmark. It is a linear equation solver. So from a mathematical perspective, not that complicated actually, but a pretty accurate representation of the kinds of computations that are being done on these kinds of supercomputers. Linear algebra, it shows up everywhere. Probably already somewhat aware of that. And that includes machine learning, large language models. That is a lot of matrix multiplication. And a lot of linear algebra kinds of applications that is happening in those models. So using a linear equation solver for a benchmark is not an unreasonable choice. And that's how they determine these figures. So you can see this is the peak. And I believe I don't want to say the wrong thing, but I think R max is more of a sustained, whereas peak is like the absolute maximum at a single moment in time that was reached. And so you can see these numbers are huge. And of course, the number of cores also just absolutely 11 million cores. Holy moly, that is a lot of cores. You'll notice though that while more cores does generally mean faster, it's not the only thing, because I can clearly see that number 6 has more cores than number 5. So number 5 is getting it done with fewer cores, right? So number of cores, yes, a factor, but not the only one. Certainly not the only one. How the cores are built, how the cores communicate, right? All very important factors as well. And so, you know, gosh, I feel like I could talk about this list for a long time, but I'll say you just one or two more things before we get back to our scheduled discussion. Somewhat political as well. You'll notice, actually, right now, the top few machines, we see El Capitan is at Lawrence Livermore National Laboratory, which is in Tennessee? California, thank you. I think Oak Ridge is the one that's right? Or am I wrong about that too? I don't remember. But Oak Ridge, number 2, and then Argonne, number 3. So all American. If you look at this list just a few years ago, or even if you scroll down a little bit on this one, oh, it's only showing me the top 10. If you look at this list from even just maybe a few years ago, like go back to June 2022, you'll see that, the US had it, but then there's Japan, there's Fugaku, there's Japan, and then China. China. So China, especially a few years ago, maybe I didn't go back, but I think maybe around COVID times, China was dominant, the top few slots. And now it's gone back in it's an arms race. There's really no other way to put it. There are very much political implications that go along with these supercomputers as well. When you think about things such as, state-sponsored attacks, attacks, digital attacks. Who has the power to run certain types of apps? Only people that have access to these kinds of super governments. So that's another aspect of these things. You won't find a lot of people. Those are all highly classified, top secret kinds of things, but still interesting, intriguing to think about, talk about. With the little information that there is out there. But this list, I think, is just reading the list by itself, maybe not terribly interesting or exciting, but when taken in context, absolutely fascinating. And we'll probably be referring to it multiple times over the course of the semester. I would encourage you to browse it and see what you can see as well in your own time. Here is the one that I mentioned. Here's some information that's about the number 2 at Oak Ridge. So you can see this is the current second place at 1,600 petaflops per second. Oh my God. Just for reference, the last time that I taught this class, I think was in 2020 or so. And if we look at, again, I know I just switched away from this list, but I can't help myself. If we go back to the list that existed around that time, we'll see that in terms of petaflops, right? The number one computer was at 513. So even just in those few years, we've managed to more than triple it. Um, and sooner or later, or actually, I mean, actually, we've kind of already gotten there. We've eclipsed 1600 petaflops. It's technically into the exaflop. Right. Scale relatively recent barrier. There used to be no computers in the entire world that could do an exaflop. And now there are multiple. That's amazing. That's incredible. And so just to give you an idea of the construction of this computer, um, oh, where'd my full screen button go though? Just do it this way. Um, we're talking about 8.7 million AMD cores compared to the ARM cores from the Fugaku. I actually think that's an interesting. Well, ARM cores, very, very. Why ARM cores have taken off recently? Do you have any ideas? It actually does have to do with performance, but I would argue it probably has more to do with traditionally very low power to Intel and AMD. Well, maybe not so much AMD. I believe ARM and AMD chips are fabricated at the same facilities, so they do share some similarities, some similar properties. Um, but ARM is certainly emerging as not just good performance, but also good power consumption, which for these kinds of computers, you can imagine is a very big consideration. For example, for one of these computers like Fugaku, I think they published that of the power that is used, which is immense, only about half of it actually goes to running the computers themselves, keeping the CPU running. Where's the other half? Yeah, to keep it cool. Yeah, those things are generating massive amounts of heat. So the amount of power consumption we're using just to keep these things from melting is so massive. That's kind of crazy, right? It's kind of insane to think about. And it's starting to hit us on a more local level with these data centers and stuff they're trying to buy. Data centers, not supercomputers. I think that's important. They're quite literally just a store of data, but still massive users of power. Um, so power consumption, very, very important concern with these computers. Obviously, do not. So governments are funding these things. Yes, they have the ability to buy massive amounts, but they don't want to be spending their money that way. They don't have to. So making improvements in power consumption, very, very important, and probably something that we'll be talking about in a future class. And so then, and even has an effect on where these are built. If you don't have the infrastructure to deliver that kind of power, if you don't have the infrastructure to provide that level of cooling, you can't build your computer. Some corporations even going so far as to build these computers on top of hydrothermal vents, so they're right on top of the source. You know what I mean? Like those are the kinds of extreme examples that you'll see with these kinds of huge machines. And so yeah, here's the latest number one at Lawrence Livermore with 11 million AMD cores. And also GPUs. That is also another, maybe not as recent, still very prevalent trend in supercomputing, using GPUs, which are very highly parallel, just kind of out of the box, right? So uh, we'll probably talk about GPUs in this class as well. But it also affects little machines. So as a more modern example, or a more small example, I guess rather, the Apple M chips printing out for the last few years. The first one that they rolled out in 2021, the M1 chip, four high performance cores on it and four cores on it. So they're trying to get the best of both worlds. Just general, checking your email, browsing the web kind of stuff. You don't need the high performance cores. You can use the energy efficient ones. But then when you want to, do a bunch of data collection, crunch a bunch of numbers, you've got those high performance cores there that will give you the power when you need the power. It's a true, system on a chip, which also includes a built-in GPU right on the die, an NPU. Anybody know what NPU is? It's a neural processing unit. Yeah, sorry, I didn't see your hand in time. A neural processing unit used for LLMs, neural networks, right, which form the basis of most of our large language models these days, and digital signal processors. So they're really trying to be the Swiss Army knife. All of these things are on a single chip, single die. So, impressive engineering feat, and that's coming from somebody who owns a PC. There's much. Still got to give them their props. Um, and these days, they've taken it even better. They've taken it to the next level. So high performance does not just matter in the supercomputing world. It's what I find most interesting to talk about in this class. But we're getting more and more high performance computing out of the stuff in our pockets, out of our laptops. That all matters too. So more and more the trends that you see, and this has been more and more true every time I've taught this class. The first time I taught this class, I would say the gap between high performance, supercomputers and your consumer grade hardware was vast. In terms of the architecture, in terms of the way that they're constructing their chips. Nowadays, that gap is a lot smaller. The kinds of chips that we're buying and using on our laptops, they're very similar to the kinds of chips that they're buying and using on these supercomputers. The biggest difference now is that they just have a hell of a lot. So, obviously I'm not going to cram a million cores into a laptop. Can't do that. So yeah, scale. Scale is really a big factor. All right. That ends the first half of the class. We are going to take a break here, as I promised. Any questions before we do that? Questions? Let's take a break. I want to try and make sure I have at least enough-ish time to get most of the way out. Always. Let's be back at, let's say 7:48. It's 10 minutes. Stretch your legs, grab a glass of water. Now I'm going to start at 7:48. I'm not 6:58. Sorry to bring the numbers mixed up. 6:58, 10 minutes. I'd be happy to chat too if you want to chat in the meantime. The plan for the last hour or so, I'm going to get all the way through these slides today. I'm not concerned about that, right? I'll pick up where I left off next time if that's what needs to happen. But what I would like to do is explain to you at a very high level the types of programming paradigms that we're going to be experiencing in this class. Mostly because I asked you earlier, and it's like very few of you have been exposed to the kinds of programming paradigms that we're going to be talking about in this class. We will be going through each of these in a lot more detail in the future. So it might seem kind of redundant for me to be doing this high-level overview now and then also going into a lot more detail later. But the reason why I do it that way is to help you when you are taking your presentation papers, because you are definitely going to be seeing these kinds of things mentioned in the papers. So even a high-level overview will help you understand the content even more. And then once we get to the respective homework assignments, we will go into each of them in a lot more detail. So the way that it works with the homework assignments, the first homework assignment, as I believe I already mentioned, is not parallel at all. It's really just to get you familiar with using the tools. How do we measure performance? How do we talk about performance? Analyze performance. Then every homework assignment after that is going to use one of the three programming paradigms that I'm about to introduce to you. So the first one's going to use pthreads as its form of parallelization. The third assignment is going to use OpenMP, shared memory programming paradigm for its parallelization. And then the fourth and final assignment is going to use MPI, which is a message passing programming paradigm library for the basis of that assignment. So we will be seeing all of these in the future in more detail. We'll actually have probably some in-class examples where you'll be able to, I'm going to give you some code examples to play around with and experiment, right, and try out to help you prep for the homework assignments. The goal for today is not to get too much into the details, but rather just to give you again, a high-level introduction to these programming paradigms to kind of set the stage for what we're going to be talking about for the rest of the semester. So let's go ahead and dive on in. Where did I put my notes? Okay, there. Starting with Flynn's taxonomy. So Michael Flynn, who is a very famous, actually just recently passed away in December of last year. But he was as I said, very well-known computer scientist on the faculty at Stanford, and was responsible for coming up with this taxonomy way back in 1866. But it's a useful piece of information that we are still using it today. If you've taken an architecture class, hopefully you're already somewhat familiar with these concepts, but I understand maybe not all of you have taken an architecture class, or maybe it's been a few years since you took an architecture class. So worth reviewing. SISD, single instruction, single data. It's your typical single core chip. So multi-core chips weren't really a thing until I want to say the 2010s when they really started to take off. They probably existed before that, but weren't around in regular usage very much before the 2010s or so. So single instruction, single data, that used to be what it was. It used to be it. You had one chip, one core on it, you had one instruction. That's what it is. Basically dead these days. You don't see chips like that so much anymore. Building custom chips used to be a very common thing. Not so much anymore. There might still be some people building some custom SISD chips for research purposes and things of that like, but I would suspect probably not a whole lot of that going on these days. Just not something you're going to see so much. SIMD stands for single instruction, multiple data. So these are traditionally on the CPU side of things. These are typically known as chips that have vector instructions, which are, if you're not familiar with, works very well with arrays. Basically, the idea is I issue one instruction that is a vector instruction, which says don't just add register 1, register 2, add the array that's pointed at register 1 to the array that's pointed at register 2. So one instruction is operating on multiple data, not just a single data. So single instruction, multiple data. These instructions exist on many traditional instruction sets. I believe x86 has vector instructions. So, still out there, still commonly used, but not really the focus of this class. We might talk about it a little bit. The big heavy hitter in this class is the third one, multiple instruction, multiple data. So now we have multiple processes or multiple cores on the same chip, even running their own instructions. So this is very much what we're used to these days, right? Our multi-core chips, very much capable of running these kinds of things, although not all programs are written to be executed that way, and some of them may still be executing in a single instruction, single data like fashion, even though the machine, the architecture that we're on is capable of multiple instruction, multiple data. But this can show up in many ways. Threading, of course, is one way that this can happen. Instruction passing, message passing is another way this can happen. And recently, this isn't a part of the official Flynn's taxonomy. In recent years, this I believe it's a woman, Frederica Grima, I apologize if I'm incorrect. Came up with an extension to Flynn's taxonomy to suggest the SPMD, which is considered a subset of multiple instruction, multiple data, where we have one program that is operating on multiple sets of data. So the way to think about traditional MIMD would be like a pipeline operation where I have lots of different steps, and the data is going to flow into the first stage of the pipeline, which is doing one operation, and then out of the next into the next operation, and so on and so forth. Whereas SPMD, single program, multiple data, is all parts of the machine are running the same program, but they might be operating on different parts of our data set. So a simple example that we're going to be looking at here in just a moment would be matrix multiplication. I can break the matrix up into chunks distribute those chunks to different cores and have those cores compute a subset of the matrix, collect those results at the end to compute my final product. That's an example of single program, multiple data. They're all running the same thing, just on different chunks of the data. This is where we live. That is where this class is living. The vast majority of the things that we're going to be talking about in this class, the vast majority of the programs we look at in this class would be classified as single program, multiple data. We may talk about streaming computing, which is an example of not SPMD, but still IMD, so not in this, but still within. That is a topic that makes discuss. But the vast majority of the things we talk about fall in this range. And then the final part of Flint's taxonomy is multiple instruction, single data. Not used too much outside of some very specific applications, but the classic example of this is what's known as a systolic array, which you can think about as being like in a two-dimensional array. The data is going to be fed in usually from one corner and then flow through the array, almost like a heartbeat, where the systolic comes from, right? It's like blood flowing through a heart. So the data kind of flows through the array of nodes, and every time it makes it to the next node, it performs a different operation on that data. So one set of data flowing through many different nodes, where each node is operating a different instruction on that piece of data. Interesting, I think. Not widely used, so not be talking about a whole lot in this class. So yeah, just kind of setting the stage for where we are. As far as programming paradigms, there are two that are very dominant within the high-performance computing landscape. We've got shared memory programming, and we've got message passing. So the two that we're talking about that are shared memory are going to be pthreads and the OpenMP library. Those are both examples of shared memory program paradigm. And message passing, we're going to be using MPI, which stands for message passing interface. Go figure, as an example of that paradigm. So some, high-level examples of the difference between the two, and we'll take a look at both these in more detail a little bit. Shared memory, what means quite literally what it says. Process 1 writes something to a location in memory. Process 2 then reads something from that exact same location. So when I say location, 5000, hexadecimal 5000, I quite mean the same literal physical location in memory. Of course, real computers are a bit more complex than that. There's virtual memory and caching and all this other stuff that gets in the way. Well, not gets in the way, but it exists for a reason. And we may talk about those things, but at a high level, the shared memory programming paradigm, from the programmer's perspective, right, which is honestly what we care about, that's who we are, it looks like the memory is shared. Is that what's actually going on under the hood? No, the operating system is doing its thing, the cache is doing its thing, and that matters. We'll probably talk about those things, but from the programming perspective, we don't have to worry about those details. It just looks like there's one block of memory. We can read to and write to different locations in that block of memory. And that's communication, right? If process 1 writes something and process 2 reads something, they have effectively communicated a piece of data. That's one of the biggest things that we're going to be talking about in this class that affects performance is communication. How does data get from point A to point B? It takes a lot of time. And if it's not done in a, smart way, it could waste a lot of time. I have to send data farther than it needs to, for example. Message passing, instead of relying on one shared memory space, has, every individual process is going to have its own space. So process 2 cannot directly access process 1's memory. Instead, if they want to communicate, they must send a message. So if I want to send a message from process 1, process 2, I'm going to issue a send call, and process 2 is going to post a receive. Now, the interesting thing here is that it's very possible that process 2 is going to try to receive a message before it even gets sent. Timing issues, anytime we're dealing with parallel programming, is something that needs to be considered very carefully. So very possible that I'm sitting here waiting for a message that hasn't even been sent yet. Of course, the negative implication there being I have to wait, right? I'm not going to proceed until I receive that message because I need that data to do whatever it is that I'm doing next. So the way we send those messages, how those messages are sent, very, very, very important if we're concerned about performance. There's lots of little traps and pitfalls like that that you can run into if you're not careful about how you construct these programs. But let's dive into shared memory a little bit more. I think what's interesting is that so there's shared memory programming, but there's also shared memory architecture. So the actual physical layout of the computer, right? And while it is true that if I'm using a shared memory architecture, I'm probably also going to be using a shared memory program on that architecture. I don't actually have to. If I want to run a message passing program on a shared architecture, that can be done. And vice versa. If I want to run a shared memory program on a more distributed system, and a more distributed architecture, then I can do that as well. But as you might expect, there are some difficulties and some inefficiencies that can arise. So in general, it is often avoided. And we do typically stick with shared memory programs on shared memory architectures and message passing programs on more distributed styles of systems, as we'll see here in a little bit. But the conceptual model of shared memory looks like this, right? I have 4 cores. This is almost quite exactly how most programmers, I think, see their laptops when they're writing code, even if it's not for a high performance computing class, right? We have 4 cores. We've got a big old chunk of memory here. And this core can access any part of this memory and this core can also access any part of this memory. It's memory in the purest sense. Now, in practice, is that really what it looks like? Well, unfortunately, real life is not that simple. So here's what it actually looks like in practice. Well, the memory may look like a shared memory. Physically, it's typically not all just one place. Physically, it's going to be distributed out. So, these individual blocks of memory live in physically different places, but from the perspective of the cores, it looks like one big job. Sure. And again, for programmers, for us, that's very nice. I don't want to worry about these details because there's actually even more under the hood than that. Caches are a thing. That's another ideally going to help us with our performance. That's why they exist, but they also have their own disadvantages if not used properly. And then there's also communication going on here, right? If the memory and the caches are in physically different locations, at some point we're going to have to physically transfer data between them. So there actually is a little network on your chip, buses, right, that are used to pass that information from point A to point B when it needs to. How does that work? Who coordinates all of that? Well, you're looking at it. So if P3 wants to access address 5000 from shared memory, from the programming perspective, it's as simple as saying do a read at address 5000. But what actually happens is the cache and the router and the interconnect all work together to figure out where that location actually is. Maybe P3 made the request, but that location is actually over here. So the operating system and all of these components are going to figure that out so that read performed properly, which adds overhead, adds performance. So those are things that we need to think about, things that we need to consider when analyzing the performance. Even though we can't see these things in the code, they're still there. They still exist and they still have an effect on the performance of the program. So we care about it for those reasons. Here's an example using this is an example using p-threads, which I believe is actually, this isn't even really a p-threads example. This is more of just like a kind of a pseudocode example of a classic matrix multiply. I think I sort of introduced this example a little bit earlier. Here is a traditional 3 for loop matrix multiplication code that you would write if you're just doing this yourself, right? Again, I know this isn't a linear algebra class, but we're taking a row of A, multiplying it by the entire matrix B to compute one row from the result C. Now, if we want to split this up, the nice thing is that each of these rows is independent of each other. So a nice clean way to do it is to take each row, or to be even more efficient, we wouldn't do it one row, we'd probably take a chunk of rows, right? And distribute those across our available processors, or available cores. So if I have 4 cores, I would chunk it up into 4, and that would give me the best performance, right? You might think so, that might be an intuitive thing, but in practice, surprise, there are other factors besides just the number of cores that go into these things. So I would expect 4 to be good, certainly, maybe close to the peak, but a few less or a few more may have a surprising outcome on that result. That's something that I hope you'll find when you work on these homeworks, right? But this is a classic example of data parallelism. If the data that I'm computing is independent, meaning, I don't need to have rows 50 through 100 in order to compute rows 0 through 49, then I'm able to take the data, split it up across the cores, and then really the only choke point then is at the very end, when I have to collect it all back together and put the pieces together to create my final result. So we can really leverage parallelism great. The downside of this, of course, is that not all problems are going to have that independent data set, right? They're not going to have the ability to chunk your data up in that way. So for those problems, we may need to try and exploit other kinds of parallelism to improve the performance. But there are many programs, many types of problems that we can do this for. And it's one of the easiest, lowest hanging fruit kinds of parallelism that exists. And an example of how this might be done in practice, each thread is assigned an ID. So, that ID is going to be a library. So we taking care of for us. We don't need to know which thread number we are. We're just going to ask, what's my thread number? And then we'll use that thread number to decide which lines we are responsible. So thread 0 is going to be responsible for lines 0 through 99. Thread 1 is going to be responsible for 100, 199, so on. So you can, of course, adjust the scale of the data set as needed. So in this case, every single processor is running the exact same code, but on a different chunk of the data. Therefore, data parallelism. This is really just an explanation, I think, of what I already mentioned. Let me make sure I didn't skip anything. Yeah, each processor reads the data, computes whatever it is that they need to compute, and then writes the result. It says hopefully a little overhead. That kind of already explained that. May not be the case. I run into a cache flush. I gotta eat that, but there's not much we can do about it. There are special languages actually that are used. I don't know if any of you have had much experience with these languages. They're a bit obscure. They're not ones that are expected many people to have access to, but there are entire languages devoted to this kind of programming called partition global address space. So another fascinating Wikipedia rabbit hole that we can go down someday, a little bit outside the scope of this class. We're going to be using OpenMP as our traditional example of shared memory programming paradigm. So OpenMP designates a master thread that the program is running on when you first start it, right? And so when it comes to a parallel section, it will spawn however many number of threads it needs to. It can be done in a number of different ways. You can say exactly, I want you to spawn 3 threads for this chunk of code, or you can let it make the decision. And oftentimes, if you let it make the decision, it's going to say, well, there's 4 cores, so I'm probably going to do 4 threads. Which again may or may not get you the best performance, right? You may need to fine tune that a little bit, but it'll do the best that it can. And so, once these threads run through the parallel section, they're going to be joined. So forks and joins, where the forks are spawning the threads for the parallel sections, which are then joined back together into the master thread for the non-parallel section. And we can do this as many times as we want over the course of our program. Actually, even though it's not really shown on this diagram, you can do all kinds of configurations with these. In fact, I could take, for example, thread number 4 and do another fork just on that. It's very possible. And depending on the problem that I solve, might be a good idea. But we probably won't be looking at problems that complicated in this class. We're going to keep it pretty simple for the homework assignments and such. The way that it shows up in the code is via pragmas. So if you're unfamiliar with pragmas, they're compiler directives. So when the code gets compiled, it will look at the information provided by the pragma and then decide how many threads to spawn, as well as some other information that is necessary for those threads to be used. Here's a simple example of what that looks like. This is a hello world example. So not as complicated as the program that you're going to get for the OpenMP homework assignment coming up. But a good example of basics where the pragma is right here. Here's the pragma. So pragma, OMP, OM for OpenMP, parallel, telling you that we want this section to be parallelized. In this particular case, we're not telling it how many threads. You can see there's an n threads variable declared, but it's not actually being set, which means we're giving OpenMP, in this case, the prerogative to decide that, or it's a variable on the system. That's an option, right? Lots of different ways that we can go about it, but within a typical OpenMP program, notice that I guess maybe bold was a poor choice because it's not showing up so well on the slides. But we actually have this extra set of curly brackets here for the pragma, right? They're not attached to a loop or an if statement. They're specifically to designate that this is this section that we want to be parallel. This is the section where we want you to fork off however many number of threads. And then this entire section of code from this top bracket to the bottom bracket is going to be run by every single thread. You might notice, though, that we do have a way to only make this section or only make parts of the code run by certain threads. So if the thread ID is 0, that's the master. So only the master thread is going to do this part. All of the threads are going to do this part, even the master thread, right? But only the master thread is going to do this part. So we can actually kind of mix and match parallel, not parallel stuff in these parallel sections. There's lots of flexibility. And then down here at the closing brace, you can see this comment indicating that while it's not specified explicitly, there is a join here. So once we hit the closing brace for the parallel section, all of those threads are joined back together. And after that point, the only thread that we had is the single master going forward. Of course, further on down, I can put another parallel section, which will form more threads for me. Join back. And I can do this as many times as I want to in a program. That's not a problem at all. And I believe, as I mentioned, I can even nest them. So I can have a parallel pragma within a parallel pragma for lots and lots of threads. But, you need to be careful about those kinds of things, of course. Here's a different example. That's not data level parallelism, showing us a different kind of parallelism using bank accounts. This is a very simple bank account structure where I'm trying to do it's like I'm trying to do a withdrawal. So if I have enough money in my bank account with this given ID to make the withdrawal, then subtract it from my bank, right? Now, in a lot of cases, these could be done in parallel because I don't expect the ID to be the same very often. It could be the same, right? So for example, if me and my wife were to both happen to show up at an ATM at the exact same time, right? And try to take out $100, then we would have the case where, I'm running this in parallel and I have two operations coming in on the same bank account at the same time. And there are implications of that, right? So thread level parallelism, we have to be very careful about how we're accessing it. We need to be careful about the order of these axes. And to illustrate, I think the next slide kind of illustrates some of the negative effects. By the way, I know I'm kind of skimming through some of these things on these slides. It's a lot of it's just for time reasons and trying to be conscious of the fact that we only have half an hour. So if I'm skipping anything that you're please holler it. I'll be happy to double back, but I'm trying to hit the high points here. So yeah, ideally, my wife and I show up, we withdraw $100, and this is how we would prefer for it to happen. One of them goes first from start to finish. The other one goes first from start to finish. So she takes out $100, and then I take out $100, and we're left with $300. That's how it's supposed to be, right? But that's only one possible way that this thing could go. We're very much in the parallel world. So when we're parallelizing things, a lot of times that means we're interleaving. It's not going to be all of process A and then all of process B. To get max parallelism, we're going to try and do as many things at the same time as we can. So they might be interleaved, or they might be even running simultaneously on different cores. That is all very possible. And so what can happen instead is something like this, where my wife shows up first. She reads the bank balance, which says $500. But before it gets to the part where she takes the $100 out, something happens. There's an interrupt. Some packets came in on the Ethernet. Who knows? Maybe the operating system threw an interrupt to do time sharing with another bajillion reasons. That's not really. But the important thing is that on a different core, my transaction to withdraw $100 is still going to go ahead. And so when I read, because her transaction wasn't finished yet, didn't get to do the final store operation where we update the bank account balance, my operation reads the old value, the old unupdated value, takes $100 off of it, and then puts the 400 back. And then whenever my wife's operation eventually comes back from the interrupt, well, it already computed the answer should have been 400, so it's going to store the same value, 400. Now, if you're me and my wife, you're like, what's the problem with that? It sounds like we just got $300, right? If you're the bank, you're not very happy about it. And then be careful, because even if you're me and my wife, too. So if I deposit money and this happens, then we're very unhappy. So those deposits are going to go through, even though you took my money. So this is not a good thing. This is a bad thing. What's this called? Anybody know? Race condition, classic race condition, right? So we have ways to deal with this. We have to synchronize the access to our account balance, which effectively means that we're going to be locking it using what's called a lock. That's a low level type of synchronization. At a higher level, you might hear them referred to as semaphores or mutexes, which are really just fancier, slightly easier to program versions of locks that provides a few more bells and whistles than your traditional locks do. At the lowest level, a lock means exactly what it says. If I'm going to enter what is called the critical section of the piece of code, which in this case would be the read and the write. I need to do both, right? Here's the read, here's the write. So this entire thing is what's called the critical section. I'm going to acquire the lock first, which means that no other process, no other threads can run this code while I'm running this code. So we've effectively locked everybody else out. And then once I'm done with this, I'm going to release the lock, which will then let other processes run through that critical section of code, assuming that they acquire the lock first. So where we put these locks is very rare. We obviously don't want to use them any more than we absolutely have to maintain data correctness, because there's, I think, a somewhat obvious penalty for using them. If we look at this updated example where the interrupt happens, notice that what happens now when I try to run my deposit after my wife's deposit gets interrupted, I can't get the lock. That's why I have to sit there and wait. And if we care about principles, so we want to, is it necessary though? Yes. I mean, if the data has to be right, then absolutely it is necessary. We got to pay that price. but we want to pay that price as little as possible. So knowing where to put those locks, knowing where to use those locks is absolutely, absolutely crucial because um, we have to avoid that penalty. We want to keep the performance up. Um, memory consistency. So when we're talking about shared, this is actually, I was kind of alluding to this earlier when I was talking about caches. Um, the problem with caches is that they become out of date, right? So the data that's in a cache is only good to me if it is actually current. And another thing, the problem that happens with caches is that it leads to me having the same piece of data at multiple locations. And so if that data comes out of sync with each other, if the value in the cache is different than what's stored in memory, for example, that could potentially lead to problems if I read the wrong piece. Now, in practice, we don't let that happen because we have cache coherence protocols, which make sure that the data that's in our caches is consistent, meaning that if the same piece of data is in two caches and one process changes that piece of data, well, I'm going to send a message over the bus or something, right? There's lots of different ways to do cache coherence. That's kind of outside the scope, but something's going to happen to notify that other cache that, hey, that copy of the data that you have is now out of date. And it'll either chuck it or get the new copy or whatever it decides to do based on the cache coherence protocol. And then memory consistency kind of takes this idea beyond cache coherence. Main memory itself. Again, who cares? It's us, the programmers. We really need memory for our human brains to keep track of all the different memory locations, all the different cache locations, and all the different ways, all the different orders that those data can be accessed. It's just not possible. That's why we have the operating system. That's why we have the cache coherence protocol, so that we don't have to think about those things. But in this class, we very much do. Not because I'm interested in the details of cache coherence, but because I'm interested in the effect that those cache coherence protocols have on the performance of my program. I can't do anything about them necessarily. You can, I think, tweak some cache coherence protocols in certain operating systems. That's a pretty advanced skill that not many people are going to do. What we can do, though, is analyze and understand those effects and be prepared to deal with them. So, yeah. So then let's take another little detour for a second, talk about different kinds of memory consistency models. Excuse me. Just a sec. Oh, okay. Yeah. So sequential consistency is classically from these types of architectures, which if you don't recognize them, that's for a good reason. They're obsolete. They don't exist anymore. Just as a little anecdote, though, when I took a computer architecture class 20 years ago now, kind of dating myself, it was on a MIPS machine. So super, but it was kind of obsolete. But you're not gonna be able to go down to Micro Center and buy a MIPS machine today. That's not what exists. So the way that these sequential consistency models work, though, is that all processors can see the loads and stores and will ensure that they are always going to be executed the same way that they are written in the program. So the loads and stores are always going to happen in the same order, which means when I'm interleaving instructions, especially when it comes to loads and stores, there are some rules about how much I can interleave them or not interleave them, might be a better way of saying it, again, to ensure that data consistency. These kinds of processors, while great for keeping data consistent, are bad for performance. You can't turn it off. It's baked into the chip. So if you're trying to squeeze the most performance out of a program, these kinds of chips they just have a lower ceiling because they're going to limit how the loads and stores can be interleaved with each other. As compared to these two more modern types of memory consistent models, which I think are more worthy of talking about, because you can see processor consistency, which is common on x86 chips, which are everywhere. says that, okay, we're going to allow the stores to be deferred until later, which allows us more flexibility when it comes to parallelizing things. My loads still need to happen in the proper order, but the stores, I'm going to allow more flexibility, allow them to be done later if I think it will lead to performance gains. And it does. That's why they chose to do it that way. But then they took that even a step farther and said, well, what if we just do Wild West out there? What if we just say, hey, anything can happen in any order? And then, what's the implications, of course, will then more about the data consistency. The theory here behind release consistency models says that while you may run into some data inconsistencies, those events will be rare, and it is faster to detect them and correct them than it is to avoid them in the first place. So the claim, that release consistency architectures are making, which I think has been shown to be effective in the literature, is to say that, hey, using the chips using our CPU chips to enforce data consistency, while it does work, is killing our performance. It's much better to not do that on the chip level, not do that on the architecture level, and have something, the operating system or some other mechanism that is going to detect those kinds of data inconsistency issues when they occur, fix. And since they are enough, it actually ends up being positive in terms of performance, which is why you see, of course, the ARM chips, which we've already talked about a bit today, are one of the chips that uses this form of memory consistency models, and is one of one of the many reasons why it's a popular. Itanium is actually, if you look at the top 500 list, another very popular chipset to use. You perhaps surprisingly, perhaps not, will not see a ton of x86 chips on top. Um, Intel, kind of struggling right now, as you may or may not be aware. ARM and AMD are really where it's at these days, and GPUs too, of course, are their own thing. So yeah, this is just more explanation of how the memory models I was talking about will restore order in that case. The big takeaway here is do not try to do this yourself. Do not try to write fences. Do not try to write locks. Do not try to enforce load store orders. Let the libraries do it. They have been optimized for its purpose. You should not be trying to do this yourself. The problems have been solved, or at least solved better than you're going to do by yourself. And I include myself in that as well. I would not be able to do a good job writing these synchronization primitives myself either. I use the library. All right. So that was kind of all OpenMP world, but threads are actually, I think, maybe a bit more primitive even than OpenMP. Here, we are actually specifically creating threads ourselves, one at a time. So we have to create threads, and then we also have to decide when those threads no longer exist and make library calls within our code to set those up. The nice advantage of doing it this way is that when we create threads, we can specify what routines we want them to execute. So typically we'll be a function, right, in our C code. Contrast that with OpenMP, where when I have a parallel section, every single thread is running that section. And yes, I can, look at the thread ID to try and do some individualization within that section. But when I'm creating the threads myself, I have a lot more direct control over that. So I can assign one thread to routine one thread to routine two. I'm doing two totally different things, but I'm doing, which is great. If they don't depend on each other, that's great. That's not data parallelism, though, right? That is pure thread-based parallelism. So I have two threads doing two different activities. Each thread has its own local set, its own local registers, its own local program count, so its own points within the point to track where it is in the program. And all of the things that we use to manage threads done through key thread library. So if we take a look at a simple P-thread example here, kind of a similar hello world, which we'll probably actually read this one next when we talk about P-threads for second. You can see that first we're going to create our P-thread pointer up here and then pass it in to the P-thread create library call. The other parameters here, besides the reference to the thread, these would be flags. This is the routine that we want the thread to run, which we can see is defined down here. And then these are arguments, which is probably one of the everybody's least favorite part of using p-threads, because arguments must be specified as a void pointer, which is just I wish void pointers didn't exist personally, but they do. The reason why is because arguments can be anything. Arguments can be any type. So we don't necessarily know what type they're going to be. And then if we actually do need to use this example doesn't use the arguments. I think I have another one on the next slide that does use the arguments. This one just spawns a thread that says, hey, the thread's running. And then the join operation here is used to terminate that thread. In which case, we're back to the single. So when we create the thread, we actually have two threads, right? The one that is running main, and then now this thread that is running foo, because main never runs foo directly itself, only through the thread. After the join, we're back down to our one single thread, which is running the main process. But back to that crazy little void pointer, here's an example that shows, kind of why it's done that way. Here we're using threads to send a little message. Again, not a complicated program, it's a toy, right? It's not doing anything computationally interesting. It's just a simple little toy showing how to create and use threads. It's going to run, this, in this case, the same function, but with a different message. So here are the arguments over here. Cast it as void pointers, and then within the function itself, cast to the actual type that we want. Clunky, it's an old system. I think if they designed p-thread system today, they would probably make some different choices. But it's been around since the 70s. And the reason why we're still using it is because it works. And there's a huge code base that uses it. So to radically change, it's a classic human story, right? Well, why do we use it? Well, because we've been using it. You can say that about lots of things. P-threads, no difference in this case. So, we have to deal with the lumps. But we get parallelism out of it. And that's not a bad thing. That's kind of what we're after. So that's a good thing. All right, let's talk about distributed memory. So this is a different type of architecture than shared architecture, where we actually have distinct distributed memory. Although the big difference between a distributed memory processor and a shared memory processor, remember, in a shared memory model, even though the memory is physically distributed, it looks to the programmer like. In a distributed system, the memory is physically distributed, but also to the programmer, P0 can only see this memory. It cannot access this memory directly, or this memory directly, or that. So, true distributed system, the memory is not shared in any way, shape, or form. The reason why we do things this way is because memory has its limits. Talk about scaling. Shared memory architectures work really well to tens or even hundreds of processors. But you saw that top 500 list. I think we were dealing with 11 million processors for the number one computer. Shared memory does not scale that. So memory limitations of shared memory architecture just aren't going to cut it for the types of massively multi-core machines that we're talking about in this class. So we need another way. And that other way is message passing. There's also architectural differences within these types of machines as well. And so, one approach is a cluster. These are actually pretty common. You'll be using the cluster one, but definitely for the second and third and fourth would be using the cluster. I guess you don't have to, but going to kind of encourage you to. Um, Clusters just use off-the-shelf parts. So same kinds of chips that you or I could buy down in Micro Center. They just buy a lot of them and they connect them using the same kind of networking technology that we might normally see. So Ethernet, they're cheap. If you use AWS for large computing purposes, you're using a cluster. Um, so this is not, however, what I would call the Fugaku machine, for example, or the top 500. They're not clusters. They take this a step farther because there are issues with clusters, and the biggest issue is the latency. With an Ethernet, we're using TCP/IP, and TCP/IP is great. The whole internet's built off there, right? It works. It's great. But if we're concerned about performance, there's some real drawbacks. All the necessary steps for dealing with the protocols. It takes time. These resources. Do we really need all of that stuff? If the only communications that we're making are within our own system, and I'm not accessing the internet, for example, do I need all of that extra protocol built on top of the system? I mean, the answer is no. So underneath the X, you can see that, well, in a true high performance system, Ethernet, not what's going to be used. TCP/IP, not what's going to be used. Instead, we're going to assume that all of these compute nodes are only going to talk to each other, and the only one we might need to designate one of them to talk to the outside world so that I can see jobs, get my results back, and things like that. But all of the other ones don't need to do that. So let's strip it away. Let's strip all that stuff away. And maybe even take it one step further and build a so in other words, I'm not just going to have a bunch of switches, these things like I would a traditional, but I'm actually going to build a custom network specifically for the system, specifically for the supercomputer. So I'm going to build it in such a way that I think is going to enable the fastest communication flows. Um, and again, we'll still use TCP/IP up here, but this custom interconnect has a lot of advantages for us. It makes routing easier. I don't have to use the TCP/IP protocol. Security is easier because I've effectively cut these computers from the outside. Right? The only way in or out is through this front end node. So yeah, I got to secure the hell out of that one, but I don't have to worry about all the other ones because they're all insulated. And so what you'll see in practice, and I believe actually Fugaku, the machine we've been talking to today, is a good example of this. We'll do something like a two-dimensional torus where each of these squares would be a router, and then these are the actual compute nodes attached. So you can see that instead of having a traditional network might look like a switch, a bunch of other things like a tree. It's not really for instead, if I have each of them wired up in like a two-dimensional grid, it also loops around. See, that's where the torus is from. This is going to lead to much more effective communication, which is going to then lead to much better performance because routing is a lot more straightforward. And I can skip all of the extra TCP/IP protocol stuff as well. And another issue, kind of related to that, is Ethernet. I mentioned latency, right? Latency being that the amount of time it takes between when the message is first sent to when it first arrives at its destination. There's an amount of time that it takes to travel along the wire. The Ethernet protocol is not built for fast communication. It's built for effective communication over large networks like the internet. So instead, InfiniBand has become the de facto standard amongst high-performance computer systems that strips away all of the unnecessary stuff that we don't need from the Ethernet protocol to squeeze as much performance out of the communication as we possibly can. They're not trying to be the internet. You're not going to see InfiniBand. Cisco. they are for specifically this type of purpose. They are trying to remove that latency. Because remember, I'm not just sending one message and when we deal with one, I'm sending thousands of messages, millions of core. Each one of them is going to have its own latency associated. So Ethernet is great at, you can get high bandwidth with Ethernet, right? I can download stuff really fast over my Ethernet connection. But the latency is what really matters to us in this class. And that's not what you're going to get out of Ethernet. So InfiniBand is definitely the de facto standard. Lots of different vendors, lots of different providers of the InfiniBand standard. Yeah. All right. Sorry, I'm aware. I know I'm skipping stuff again. I'm just trying to be aware of the time. In fact, I'm almost wondering if I should stop here and pick up next time because I just don't think. Yeah, I'm gonna stop here and pick up where we left off next time because I don't think I'm gonna have enough time to do this justice in minutes, and I would rather take the time to do it right than go through. So, thank you all. Be happy to stick around if you want to chat. Any questions, although you've been 2.5 hours, so I certainly understand. If you're ready to get home, I am as well. It's nice to meet you all, though, and I'm really excited to work with you all this summer. Thanks. I did record this, by the way, and I will make sure this gets posted to Canvas probably tomorrow.